All right, let's talk about a programming language that didn't just show up to the party. It completely redesigned the house. We're digging into Java, a language that was born at the absolute perfect moment to solve the internet's biggest growing pains and, really, change software forever.
A revolutionary force. You know, that's a pretty bold claim. But honestly, it's not an exaggeration. See, Java showed up just as the early internet was hitting a massive wall, facing this huge problem that really threatened to stop its growth dead in its tracks. So what was this problem that needed a full-on revolution to solve it?
To really get why Java was such a big deal, we've got to rewind to the early 90s. The internet was just exploding, right? Connecting all these different computers into this highly distributed universe. The problem was, the software we were using was built for a world of lonely, isolated machines. It just wasn't ready for this new interconnected reality. So developers were staring down two huge hurdles. First up, portability. Back then, code was basically chained to its hardware. A program you wrote for one computer was completely useless on another. And second, security. I mean, in this new world where you're downloading programs, how could you possibly trust that the code from some random server wasn't going to be malicious? This was the exact puzzle that Java was designed to solve.
So how did Java manage to solve both of these massive problems at the same time? Well, it all comes down to a single brilliant idea at its very core. Let's take a look at this magic ingredient, something called bytecode. Okay, here's where the genius comes in. When you compile a Java program, you don't get code for a specific computer chip. Nope. Instead, you get this intermediate language called bytecode. It's written for this theoretical, virtual machine that doesn't actually exist as a piece of hardware. And that simple idea, right there, changes everything.
This three-step process was the key. A developer writes the code just one time. The compiler turns it into that universal bytecode. And then, the Java virtual machine, or JVM, that's sitting on any computer, a Mac, a PC, doesn't matter, it acts as a real-time translator. This is what gave birth to Java's famous motto, write once, run anywhere. But it also solved the security problem. Because the code is running inside this virtual machine, the JVM acts like a security guard, a sandbox, that stops the code from messing with parts of your computer it shouldn't. It was an absolutely brilliant two-for-one solution.
But just solving the run anywhere problem wasn't quite enough. As programs were getting bigger and more connected, they were turning into these tangled, complicated messes. So Java tackled this problem head-on by championing a really powerful design philosophy called Object-Oriented Programming, or OOP for short.
OOP is built on these three pillars. You can think of them as a set of rules for building digital objects, almost like Lego bricks, that hold both their own data and the tools needed to work with that data. These three principles all work together to make code more organized, much easier to reuse, and way less likely to break. Let's talk about encapsulation. This is like building a protective shield. You bundle your data and the code that messes with it into a single self-contained object. This stops other parts of the program from just reaching in and messing things up when they're not supposed to. And the source material gives a perfect real-world analogy for this.
It's just like the automatic transmission in a car. It is incredibly complex inside, right? But you don't need to know any of that. You have one simple, well-defined interface to use it, the gear stick. That's encapsulation. And the other two principles just build on this amazing idea. Inheritance lets you create a new, maybe more specialized, transmission that gets all the features of the original one, while polymorphism lets you treat all different kinds of transmissions the same way, just through that simple interface. Together, they create this powerful system for building really complex software that doesn't just collapse under its own weight.
So, we have these big ideas, like objects and bytecode. But what do the actual instructions that build these things look like? Let's peel back one more layer and just take a quick peek at the fundamental building blocks of a simple Java program.
Now, you don't need to be a programmer to get the logic here. This little code snippet uses a basic command called a for loop. It's just telling the computer, hey, start a counter at 0, and as long as it's less than 10, print a line of text and add 1 to the counter. This kind of simple, repeatable logic is the foundation of pretty much everything a computer does. And that simple loop, it produces this result, 10 lines of text, counting from 0 up to 9. These loops and the data they work with are the absolute bedrock of programming. So let's look at the kinds of data Java actually uses.
That variable x we just saw, that was an int, or an integer. Java programs are built using all sorts of raw materials, whole numbers, numbers with decimals, single characters, and simple true or false values. Every complex app you've ever used is, at its very heart, just a clever combination of these basic data types.
But look, creating a revolutionary language is one thing, staying relevant is a whole other ballgame. The internet and computing have changed so dramatically since the 90s, and for Java to survive, it had to evolve right along with them.
And a pivotal moment in Java's evolution was the release of J2SE5. The source material calls this update revolutionary, and for good reason. This wasn't just a minor improvement. It was a fundamental expansion of what the language could even do.
And these were not just minor tweaks. Each one of these features was a major upgrade. For instance, generics helped developers write way more flexible and bug-free code, while the enhanced for loop made everyday tasks so much simpler and easier to read. This commitment to real, meaningful evolution is why Java has stayed so relevant for so long.
But Java's true legacy isn't just about the code that's written in it. Its biggest innovations, that portability through a virtual machine, the focus on security, the object-oriented design, they were so powerful they became the new benchmark. They created the blueprint for what a modern programming language was even expected to be.
I mean, you can see Java's DNA in countless languages that followed it, like C#. Its core concepts, from the virtual machine all the way to how it manages memory, just became industry standards. So Java didn't just succeed on its own, it literally laid the foundation for the entire next generation of programming languages.
So, Java gave us the perfect answers for the challenges of its time: portability and security for a brand new connected world. Which leads to a final really interesting question. As we face today's frontiers, AI, decentralized systems, quantum computing, what are the fundamental problems that the next revolutionary language is being designed to solve right now? Thanks for digging into this with me.